has been there for a little over a year now, I guess, right? So he's a second grader as a graduate student. And you'll find that he's extremely sharp, especially for a second year graduate student. He was an undergraduate in Wisconsin, did some work with Ellen's rival there. He went and did a part 3 at Cambridge, at which time he also worked with Mike Proctor there. And now he's working with Elliott Quadrant at Berkeley, and he's done some good work on Rayleigh-Taylor Instability and other things. So, explore.
Thanks. So I'm going to talk about Rayleigh-Taylor Instability and Dilute Plasmas. So this is work I did with Ian Parrish and Elliott Quadrant, and most of these results are in a paper that was recently accepted into monthly notices, but not quite published yet. So first I'm going to talk about where in astrophysics these things are important, and then tell you a bit about the physics of dilute plasmas, and then kind of get into the meat of things. So first thing, what do I mean by Rayleigh-Taylor instability? Throughout this presentation, I'll refer to it as RTI for short. What I mean is that you have a contact discontinuity. That is a place where the pressure is continuous across an interface, but there are discontinuities in density and temperature. And you also need there to be a gravitational field or some sort of acceleration. And if the acceleration is going downwards, and you have heavy stuff on top of light stuff, the heavy stuff wants to fall through. That's what I mean by Rayleigh-Taylor instability. So you're unstable if the density of the upper material is larger than the density of the lower material. Okay, so where do we find contact discontinuities in astrophysics? I'm going to give 3 carefully chosen examples. The first is supernova remnants. So there's this very nice blast wave solution of supernova remnants. In general, if you have an explosion that happens in a small area, you get this self-similar solution. There's a couple features of these solutions. One is that you have 2 shocks. You have an inner shock and an outer shock. So at these shocks, kind of all the quantities of problem are discontinuous. So the pressure, the density, the velocity are all discontinuous at the shocks. And then in between, you have a contact discontinuity. So at this location, the density changes, so it drops by quite a bit, but the pressure is still continuous. And the really cool thing about this solution is that it's self-similar. So when you normalize everything properly, if you normalize the lengths to the radius of the outer shock and all the other quantities appropriately, everything kind of expands outward self-similarly. So Rs goes as t to the 2/5 power, and all the quantities, when normalized properly, look the exact same no matter what time you look at them. In this problem, you have an acceleration that's outwards. So to the inner side of the contact discontinuity, you're at high density, and on the outer side, you're at a low density. Since the acceleration is to the right, that's unstable. And you can do simulations to see what the Rayleigh-Taylor instability looks like. And just as the whole problem is self-similar, the Rayleigh-Taylor instability is also self-similar. So in this fairly old paper, Chevalier and others initiated their blast wave solution with a small perturbation at a time t0, and then they solved the fluid equations on an expanding grid. And you can see that at later times, through many decades of time, the results are pretty much the exact same. So everything's expanding self-similarly, including the Rayleigh-Taylor instability. Another example in astrophysics where you get contact discontinuities are in the solar corona. If you imagine a magnetic flux loop, the flux loop has some magnetic field and some pressure on the inside. outside the flux loop, you can say that the magnetic field is 0, but the flux loop is in pressure equilibrium, which is that the total pressure, which is the gas pressure plus the magnetic pressure, are continuous along the flux rope, and that means that the gas pressure outside is different from the gas pressure inside. And this is a really easy way to get contact discontinuity because if the gas pressure is different, probably the temperature and the densities are different. But the total pressure is continuous. So this is a place where you can get Rayleigh-Taylor instabilities. And the last example that I want to give is cold fronts in galaxy clusters. So, can you guys see where the cold front is on this intensity map? This is a Chandra image of some cluster. There's a discontinuity in density, and it's actually along here. I don't know if you can see it before I pointed it out. Here's another example. Here there's actually two cold fronts apparently. One is up here. There's another one down there. So to me, it's not obvious where there's a cold front or not, but you can do some analysis, and here are maps of the surface brightness that they measure. It's the black points, and then they assume that there's some density profile that looks like this, and they have some way of figuring out what sorts of surface brightnesses you would get given a certain density, and from that model with these positive density profiles, you end up very well reproducing the data. So this indicates that there is kind of a density discontinuity at these interfaces. And you can also see what the temperature is doing by looking at the spectra. And it turns out that the pressure, or that the temperature is also discontinuous across this interface. And the pressure discontinuity and the density discontinuity act in such a way that they cancel out, so the pressure should be continuous. So the temperature and density are discontinuous, but the pressure is continuous, so these are contact discontinuities. Okay, now I want to shift gears a bit and talk about dilute plasmas. So in general, if you want to use a fluid approach, you want to make sure that the mean free path between collisions is short in comparison to the length scales in your problem. So the length scales on which kind of big things are varying, like magnetic fields or pressures. However, in plasmas, there's another potentially important length scale, which is the gyro radius. So you have your ions and electrons gyrating around magnetic fields as shown here, and there's a length scale which tells you about how big these gyrations are. And the ordering that I want to consider is one in which the gyro radius is very small in comparison to the mean free path. So here you have a particle gyrating, and it undergoes many gyrations before it undergoes a collision. However, I still wanted to be able to use the fluid equations. So for that to be true, I want the global length scale of the problem. So here the magnetic fields are kind of varying over this long length scale. That should still be much larger than this mean free path. And if you satisfy this sort of scaling, what's happening is that your particles are, they basically look like beads on a string. So they're more or less confined to magnetic field lines. And most of the collisions that they make are going to be along field lines. So they're going to interact with the other particles that are on the same field line. And so if this sort of scaling is satisfied, the transport will be anisotropic. And the transport phenomenon that I'm mostly interested in here is going to be heat transport or temperature conduction. And it turns out that you end up with this anisotropic heat flux. So you get a heat flux, which is only in the direction of the magnetic field, which I call EV. And it's only due to temperature gradients along the magnetic field. So the flux is along the magnetic field and only due to gradients along the magnetic field. There's a heat conductivity kappa, which can be turned into a diffusivity chi. So this is something that has units of length squared over time. So with this chi, you can come up with a diffusion or a heat conduction frequency. So this is the conduction frequency that I'm going to use a lot in this talk. And you can estimate what this is. So a diffusivity is like a speed squared over a frequency. And the heat is carried by the electrons. So a good speed is the electron thermal temperature, and then the frequency would be the electron collision frequency. And it turns out that chi goes as, so the thermal diffusivity goes as T to the 5/2 over n. So this is an effect that's important when you're hot and when you're dilute. So this is why I was talking about dilute plasmas. So plasmas in which this effect is important. Okay. And you might wonder, so is this actually important for astrophysics? And the answer is that I picked 3 examples in which it is important. So if you take some kind of typical numbers for temperatures and densities in supernova remnants, or the solar corona or in galaxy clusters, you find that in each case, the electron collision time is much longer than the gyration time, which means that you undergo a lot of gyrations before you collide, and that means that this anisotropic conduction is an important effect in your problem. So the heat conduction really is going to be along field lines, and this isn't. I mean, the difference between these scales is orders of magnitude. Okay, so now I want to talk about the Rayleigh-Taylor instability. And first I'm going to do the linear theory and then the nonlinear theory. So first for the linear theory, I want to talk about the classical problem, which is when you have these 2 layers at constant density, rho plus and rho minus. You have a discontinuity at the order at z equals 0. And I also want to do this problem in the Buoyancy approximation because it simplifies things. So these are the equations that I'm solving. I have a continuity equation, a momentum equation. This is the induction equation. And then the energy equation is just conservation of entropy by the fluid, except due to a heat flux, which I will assume is anisotropic. And in order to close this system, you need an equation of state, so I just pick ideal gas with gammas 5/3. So it makes things easy. Problem is hard enough as it is. So the classical problem, I'm not going to consider conductivity for now. I'm just going to do this kind of easy warm-up problem. So there's 2 steps to deriving the Rayleigh-Taylor dispersion relation. The first step is to look at what the perturbation is doing on the 2 sides of the contact discontinuity. So it's not so hard to manipulate the momentum and energy equation to get this equation for the perturbation of the vertical velocity, that I call delta UZ. And the solution looks like this. So there's kind of like 2 modes, one which is increasing exponentially with height and one which is decreasing exponentially with height. The second step is to apply your boundary conditions. So there's 4 boundary conditions that you need because you need to say what A is, what A plus and A minus is for the upper and lower layers. So that's 4. However, this is linear theory, so the overall amplitude doesn't matter. So there's really only 3 constraints on what the A's are, and then the last boundary condition will give you the dispersion relation. So the first three boundary conditions are pretty easy. We want the perturbation to go to 0 at infinity. And you also want that the vertical velocity at the interface should be continuous, because otherwise the interface wouldn't stay as an interface. Applying these, you end up with this solution. And this says that if you are above the interface, so if z is positive, your perturbation decreases exponentially with height. And if you are below the interface, so when z is negative, you have that the interface decreases exponentially as you go down. Okay? So you have that the perturbation is continuous at z equals 0, but the vertical derivative of the perturbation is actually discontinuous. And there's kind of only certain values of this which is allowed, and that's what gives you the dispersion relation. So you can derive this by integrating some form of a momentum equation across the interface. You end up with this equation. And when you plug this solution in to here, you end up with this dispersion relation. And this is the classical Rayleigh-Taylor dispersion relation. So there's a couple things to note. One is that omega squared is negative when A is positive. A is called the Atwood number. It is proportional to the density difference across the interface. So if the density above the interface is greater than the density below the interface, then the Atwood number is positive, and you get an unstable contact discontinuity. And for later on, I'm going to be thinking about temperatures as well, because the anisotropic conduction has all to do with temperature, and it's important to realize that the change in density is kind of the opposite of the change in temperature, because the pressure is continuous. So if the density above the contact discontinuity is greater than the density below the contact discontinuity, then the temperature above is less than the temperature below. Another important thing about this dispersion relation is that we have this UV catastrophe. So as you go to smaller and smaller wavelengths, your wave number gets larger, and it looks like the growth rate could increase without bound. And so in physical systems, there's going to be some sort of small-scale physics which gives you maybe a viscosity or a surface tension, and that will give you and that will select out a scale at which you have the largest growth rate. So you have like your small-scale physics which solves your moving catastrophe. Okay, so now I'm going to do the problem with anisotropic conduction, and since the conduction cares a lot about temperature, so that the free energy source is temperature gradients, instead of doing a constant density layer, I'm going to do an isothermal layer, so that the only source of free energy is what's going on at the interface, and there's no kind of free energy in the layers themselves. So in that case, I have temperature T plus and density rho plus above the interface, and temperature and density T minus and rho minus below the interface. But for an isothermal layer, the density is also changing. So when I refer to rho plus and rho minus, I'm actually only talking about the density right above or right below the interface. The temperature, however, is the same no matter where you are, as long as you stay above or below the interface. So you end up with the density and the pressure, which have this exponential decrease with height. That's whatever this is the solution when you have an isothermal layer. And then the other key thing is that I'm going to consider a very weak horizontal magnetic field. So I'm going to assume that the magnetic field is not dynamically important, but only sets the direction for the anisotropic conduction. I couldn't have a vertical magnetic field because otherwise I wouldn't start off in equilibrium, because you could get conduction along the magnetic field line because the temperature changes on the two sides. So I'm going to do the exact same procedure as before, except I'm no longer going to assume the Buoyancy approximation, so I'm going to consider the fully compressible equations. Turns out that the perturbations in the isothermal layers have the same form as before, so you get this exponential dependence with height, but now these wave numbers are a bit more complicated, so that this is what you end up getting. And the key thing here is that the conductivity only comes in one place, which is this ratio R, which is the ratio between the time for pressure adjustments over the time scale of density adjustments. And R kind of looks like 1 over gamma. So if there was no conduction, so if omega c, the conduction frequency was 0, then you can see that R is just 3/5, which is 1 over gamma, since I picked gamma as 5/3. However, if omega c is very large, if conduction is very fast, R approaches 1. And if conduction is very fast, that means that the perturbations are isothermal, and isothermal perturbations are kind of like having gamma equals 1. So this R looks like a 1 over gamma in the two limits of either very fast conduction or very slow conduction. And in between, it's in general complex. So you can solve for the vertical structure of the perturbations away from the discontinuity, and as before, you can derive a constraint on the vertical discontinuity of the vertical derivative of the perturbation, and that will give you the dispersion relation, which looks like this, and it's just a complicated mess. So in this dispersion relation, once you kind of normalize out everything you can, there are three parameters. One is the Atwood number, so that tells you how big your density contrast is. Another is KH, which sets how compressible your mode is, and then the last is how strong conduction is, which I parameterize as omega c over omega RTI. So omega RTI is the growth frequency of the classical Rayleigh-Taylor instability. So you have this complicated dispersion relation, and once you pick these values, you can ask Mathematica what growth rate you get. I've done that here. So here I've picked A is equal to 1/2, and I've plotted the growth frequency normalized to the growth frequency of the classical instability as a function of KH. So if KH is large, you're in the local Buoyancy approximation, and all the lines which correspond to different values of the conductivity all approach 1, which is to say that the growth rate hasn't changed at all when you introduce the conductivity. And this is true even for large conductivities. So when omega c over omega RTI is about 10, it's in the fast conduction limit. So if you increase above 10, you get the exact same result. For small KH, your modes are extremely compressible, and the growth rate becomes small, and you do start to get differences between the dispersion relation for the isothermal perturbations when omega c is large, and the adiabatic ones when omega c is small. So I want to say a little bit more about these two limits. So first, the local limit, where kh was large, there's no change from the classical result. And it turns out that this is because, in the Buoyancy limit, it turns out adiabatic motions are also isothermal. So if you're Buoyancy, the perturbation of the pressure is very small in comparison to the perturbation of the density and the perturbation of the temperature. So if you're adiabatic, that means that the perturbation of the density is small. But from the equation of state, the perturbation of the density is very close to the perturbation of the temperature. So if this is small, then the perturbation of the temperature must be small. And when I say small in the Buoyancy approximation, I mean it's of size about 1 over kh. So if kh was 10, as here, the temperature changes are about 1 over 100. For larger kh, it's even smaller. So in the Buoyancy approximation, conductivity doesn't matter at all because the motions that you had before conductivity were actually isothermal, so conductivity doesn't change it. Now, the opposite limit, when you are extremely compressible, when you have very small kh, it turns out that omega is linear in kh. So as you get to smaller and smaller kh, that is when your growth rate becomes larger and larger in comparison to the density and pressure scale heights, you have a smaller growth rate. And a way of understanding this is that the energy in the perturbation, if you're very compressible, can go into compressions opposed to, say, kinetic energy that would grow the instability. So if your modes are very compressible, then you grow less quickly. Now, in this case, the conductivity does make a difference. So you could ask, how much of a difference does it make? It depends what the density ratio is on the two sides of your interface. So if you have a large density ratio, it turns out that conductivity doesn't make much of a difference. So here I plotted omega over kh. So omega approaches this value as kh goes to 0. So that there's kind of two limiting regimes. One where you're isothermal, so the conductivity is very large, and one is adiabatic, and the conductivity is very small. And everything in between is bracketed by these two values. So for a very large density contrast, see that actually makes a big difference or it actually rather makes a very small difference if you are conductive or not. However, if your density contrast is small, you're in the opposite limit, and isothermal perturbations, so perturbations with large conductivity, are actually, they grow quite a bit faster than the perturbations that are adiabatic. And this kind of makes sense. If your background is isothermal, isothermal perturbations are marginally stable. However, adiabatic perturbations on an isothermal background are stable. So you would expect that the isothermal perturbations would have a larger growth rate. Okay. So now I'm done with the linear regime, and I'm going to talk about what happens when you look at the nonlinear regime. So I ran a bunch of simulations in Athena, where there's no explicit viscosity, so all my viscosity is just numerical. I have a box that is horizontally is a square of length L and goes L above z equals 0 and L below z equals 0. So it's like two cubes stacked onto each other. I pick A is equal to 1/2. This ratio is kind of like kh, which I've set large. That means that I'm kind of trying it to be in this Buoyancy limit where compressibility is not very important. I start with a very small initial magnetic field, and the perturbation I use is a zone-to-zone random number with a vertical smoothing so that the perturbation at the upper and lower boundaries goes to 0. And the perturbation that I start with is about 1% of the sound speed. Okay, so there are 4 regimes that I investigated, and that's because you can start with a magnetic field that was initially horizontal or vertical, and then your contact discontinuity can either be Rayleigh-Taylor stable or unstable, depending on the which is bigger, rho plus or rho minus. So in this top row, you're Rayleigh-Taylor unstable, and then in the bottom row, you're Rayleigh-Taylor stable. And for a vertical magnetic field, there's this extra instability called the Heat-Flux driven Buoyancy instability that I'll get to later that can come in this regime. Okay. So before I talk about what happens with conduction, I'll mention a bit about the problem without conduction. Bidimensional analysis, if you say the only dimensional parameter in your problem is the strength of gravity, you would say that the height of the bubbles in the nonlinear regime should increase as gt squared. So what do I mean by height? So in practice, what I do is that I have some simulation results. So this is like temperature in my simulation box, and I take horizontal slices, and I end up with a profile that looks a bit like this blue line. And then I pick a reference value, which in this case is 99, and I ask where is the temperature, the horizontally average temperature equal to 99, where it started off at 100. Okay? So in this case, it would be right here. So I would say that this vertical position is the height that the bubbles have reached at this time. So this is my definition of height. And then, so this is kind of what the temperature contours look like for the simulations without conduction. And you can see that initially you have these bubbles that are rising that are very small. There's these little mushroom caps at the end, which are due to little Kelvin-Helmholtz instabilities that occur as the perturbation is rising upwards. And as time goes on, the height increases and the bubbles merge and form larger bubbles, as shown here. Now I want to try to show some simulation of this. Computer would work.
Ignorance.
Yeah. Let's see.
They worked like 5 minutes usually long.
Yeah, I don't know what's going on.
Probably both of them watching.
What is all this? Sorry? It's actually an old computer commercial, so this computer is very old, doesn't work so well. I guess this is a good argument now that I should get a new computer. Okay, so hopefully this works now. So here's a simulation of temperature contours. They start as small bubbles. They kind of join together and become larger as
That's what, which case is this?
this is without an introduction.
Not surprisingly, but it's a little bit like fire.
Okay. So now I'm going to show what happens when you include conduction. So this is what happens when you have a horizontal initial magnetic field and a Rayleigh-Taylor contact discontinuity, which is Rayleigh-Taylor stable. In this case, there's no instability, so you would think that the height would stay close to zero for the entire simulation. However, these simulations show that the height is actually increasing, and that's due to numerical issues. So what's happening is that even though the magnetic field starts off horizontal, I put in a random perturbation, which will give some small vertical component to the magnetic field. And the small vertical component can then conduct heat vertically. So you actually get perpendicular conduction due to this numerical mixing effect. And what's actually happening is the entire interface is actually moving upwards. And the reason why that happens is actually due to pressure imbalance. If this is the interface, now the temperature above the interface is larger than the temperature below the interface. There's also a density difference, but the pressure is continuous. It's a contact discontinuity. If you allow there to be a bit of temperature diffusion, then the temperature above will decrease by a bit and the temperature below will increase by a bit. The density stays constant on short time scales, so in order to satisfy the equation of state, the pressure must decrease above the interface and increase below the interface. So you actually end up with a pressure pushing upwards. So the entire interface moves upwards due to this diffusion.
So that would be a physical effect in terms of external noise.
Yes, or if your initial magnetic field was not perfectly horizontal, it had a small vertical bit, then this picture still holds. This is what the height looks like as a function of time if you have also a horizontal magnetic field, but with a Rayleigh-Taylor unstable interface. And in this case, there's kind of two regimes. Initially, it doesn't make any difference if your contact discontinuity was stable or unstable. And that's because your height is increasing just due to diffusion. In this case, it's due to this perpendicular diffusion due to these numerical issues. Or kind of physically, it would be because the magnetic field isn't exactly aligned with the interface, that there's a small component perpendicular to the interface. And so initially, diffusion is most important. However, at later times, the Rayleigh-Taylor instability starts to grow, and the height increases much as in the case where you didn't have any conductivity at all. And this is kind of a generic picture. So conductivity always wins at early times because the height due to conductivity goes as root t, whereas the height from Rayleigh-Taylor is supposed to go as t squared. So at early times, root t is going to be greater than t squared. So initially, you're dominated by diffusion. At late times, it's Rayleigh-Taylor. And now I'm going to try to show a simulation again. And hopefully my computer won't die. So this is a simulation with the diffusion. And you can see at early times, there's this spreading just due to diffusion. And right now is when Rayleigh-Taylor wins and the height increases due to Rayleigh-Taylor. You can see that the bubbles are much bigger because the simulation is more diffusive. Okay. And here's just two snapshots. You can see initially you have these small bubbles, and again they're merging together to form larger bubbles with Rayleigh-Taylor instability. Okay. The next case that I want to look at is when you have a vertical magnetic field. And in this case, I'm looking at a Rayleigh-Taylor stable contact discontinuity again. Here I applied the height as a function of time. The solid lines are for anisotropic conduction, and the The dashed lines are isotropic conduction. So the isotropic conduction, the height just increases as square root of t. However, for anisotropic conduction, and this dotted line is for a higher resolution simulation, you actually see that the height increases less quickly or more slowly at later times. And this is due to this other instability that I alluded to before, the heat-flux-driven buoyancy instability, which I want to talk a little bit about right now. So this is an instability that you get if you have a high temperature above low temperature with a vertical magnetic field. So there's a heat flux that's going downwards. And this heat flux is actually unstable. So if you introduce some perturbation with a wave number that is it has some vertical and horizontal component, as shown here, these perturbations will bend the magnetic field lines like this. And then these bent magnetic field lines will produce temperature changes due to the divergence or convergence of the heat flux, which is due to the divergence or convergence of the magnetic field lines. So the places where the field lines are parallel, like around here, there's the flux, the heat flux is neither converging or diverging, so you would get zero. The divergence of the heat flux is zero here, and similarly around here, the magnetic field is also parallel, so you get zero heat flux here. Here I've labeled the locations where you have zero. There's no heating because the field lines are perpendicular, or are parallel rather. Sorry. And if you look, you can see that these locations correspond to where the perturbation is zero. Where the magnetic fields are converging, like over here, where the heat flux is going downwards, so over here, the heat flux is converging, you get heating. Here, the heat flux is diverging, the magnetic field lines are diverging as you go downwards, so you get cooling. So here I've labeled with the plus signs the places where the magnetic field lines are converging, and you can see that those are all places where the perturbation is going upwards. So if you have perturbation that's going upwards, the field lines converge, the divergence of the heat flux, or you get convergence of heat flux, that means that you're heating up. So you have a perturbation that goes upwards and gets heated up by this heat flux, and it heats up more, so it goes upwards more, and it's unstable. Likewise, here the field lines are diverging as you go downwards, so you get a divergence of the heat flux. So the perturbation here is cooling down, and that means that it's going to continue to sink. And so this is a perturbation that started off going downwards and it's going to continue to sink because of this divergence of the heat flux. And you can show that in the fast conduction limit, you basically get that the density change is given by if you moved upwards or downwards. So what does this actually do? Again, I'm going to test my luck and see if I can show a movie. This is a movie made by Mike McCourt, a student of Elliot's at Berkeley. So here we have a high temperature on top, low temperature at the bottom, and a vertical magnetic field lines. So this is the case that's unstable to the heat flux driven buoyancy instability, the HBI. And you can see that what the instability does as it saturates is that it takes the vertical magnetic fields and realigns them to be horizontal. And when you have these horizontal magnetic fields, they aren't going to carry a heat flux anymore because the temperature here is about constant because they're horizontal. So what this instability does is that it takes vertical field lines, turns them horizontal, and it turns off the heat conduction. So when you start off with a hot thing above a cold thing, you initially have some conduction, but then this instability turns off the conduction so that you have installation.
That was a 2D calculation.
That was 2D. It's much easier to see what these things are doing in 2D than this 3D. So this is the graph of height versus time again. And you can see that when you have anisotropic conduction, which is the only case in which you get this stability, at late times, because of the HBI, the field lines have reoriented to horizontal. They can no longer conduct as much, and thus the height increases slowly at late times. And you can actually show that the height should actually saturate to a fixed level. You can't see it in the simulations because there's this numerical effect that even if you did have a fairly horizontal magnetic field, due to numerical mixing, you would still get some perpendicular conduction. Okay, and then the last case is where you have a vertical magnetic field and a Rayleigh-Taylor unstable interface. And this looks a lot like the case with a horizontal magnetic field, where initially you're dominated by diffusion, and then at late times, Rayleigh-Taylor takes over. So here's the picture of what's happening. In all cases, you have diffusion that is occurring, whether it's diffusion along field lines or perpendicular to field lines, and physically, this perpendicular diffusion could be due to the field line not being perfectly aligned with the interface, or it could also be because there is actually some perpendicular diffusion, though it's fairly weak for these hot dilute plasmas. If you're Rayleigh-Taylor unstable, you get the Rayleigh-Taylor instability at late times, diffusion wins at early times, and if you are Rayleigh-Taylor stable, then for the vertical magnetic field, you have the Heat-Flux-driven buoyancy instability, the HBI, which reorients you into a horizontal magnetic field. So now let's consider these three applications that I gave at the beginning, and look at where they correspond to on this diagram. So for supernova remnants, you're unstable, but the supernova remnant problem is kind of different from this Cartesian case which I gave before, because the acceleration is due to the fact that you have the shock that's moving outwards, and the contact discontinuity is moving outwards, and the acceleration is actually decreasing with time. So in this case, it's actually, the Rayleigh-Taylor instability is actually more prominent at early times, and diffusion would be more important at later times. And in general, because there's a new dimension-full parameter in the problem, the temperature diffusivity, the problem is no longer self-similar, so you would expect to have this nice self-similar solution anymore. In the solar corona, you are also Rayleigh-Taylor unstable, but your field line is horizontal, and by horizontal I just mean that it's aligned with the interface. So in that case, you expect to get this some sort of perpendicular diffusion and the Rayleigh-Taylor instability at late times, the conduction time for kind of the typical densities and temperatures in the solar corona is actually very short in comparison to the lifetime of these flux loops. So the conduction time is like minutes, whereas the flux tubes can last for hours or even longer. So if there's any diffusion across the flux tubes, it would have to be rather small for them to stay coherent, which we observe. Another thing to point out is that in this problem, the magnetic field is a really dynamical effect. whereas the simulations I ran, the magnetic field was very small. So that's another important effect that you have to consider if you're interested in this problem. For the cold fronts in galaxy clusters, the magnetic field is, if you imagine that it's initially vertical, you expect that this density change to be Rayleigh-Taylor stable. So you're in this regime where you start off having diffusion, but that gets cut off by the HBI. So you would expect that the height that the layer, or the width of the layer that you would end up with scales like this. For kind of typical parameters, you would guess that you would end up with a width or a height of about 40 kiloparsecs, give or take a bit. If anything, it should be larger than this. So the factors of order unity that I've ignored will probably make this larger. However, they are observed to be less than 10 kiloparsecs. And you could ask, well, how could that be? One thing is that the magnetic field might not start off vertical. It might actually start off fairly aligned with the interface. In that case, the conduction, being anisotropic, would keep the layer fairly thin. But for kind of random values of the initial magnetic field, you would expect this thing to diffuse out much more than is observed. So some people propose that the reason why you get these very sharp discontinuities in the observations is due to this heat-flux driven buoyancy instability, but it's kind of unclear if this is good enough. You might need something else to confine the layer to a very small size. In the last little bit, I want to say a little bit more about just the plain old Rayleigh-Taylor instability without anisotropic conduction. Earlier in the talk, I said that the height of these Rayleigh-Taylor bubbles should increase as GT squared. And this is motivated from dimensional analysis when you say that the only dimensionful parameter in your problem is gravity. So I wondered, does H actually go as T squared? So what people always do in the literature is that they make plots like this where you plot the height as a function of T squared. And people say, well, at later times, these lines look fairly horizontal. These are just for two simulations that I did of the Rayleigh-Taylor problem without conduction. However, if you plot this on a log-log plot, you see that although the height might initially increase as T squared, at late times it's actually increasing as T. So you might wonder, how does this happen? I mean, from dimensional analysis, the height should go as T squared. What was wrong in our analysis? So to see what might be wrong, you might wonder what happens when you change the resolution. This is the height as a function of time for 3 different resolutions, and kind of worryingly, they actually look very different. Now, you can actually fix this problem by, instead of normalizing your lengths to L, by normalizing your lengths to the size of the initial dominant mode. So as I said before, this Rayleigh-Taylor instability has a UV catastrophe, but if you have some sort of diffusion, in the case of Athena, the diffusion is just numerical viscosity or numerical diffusion, that sets a length scale of that's growing the fastest in the linear stage. And when you normalize your lengths to that length scale, you see that the 3 simulations of different resolution actually line up fairly well. What this means is that the simulations actually remember what the size of the initial perturbation is, even very late into the nonlinear phase when the bubbles have merged by quite a lot. So there's this new dimensional quantity that, that is important in your problem, which is the size of these initial dominant modes. And if you have another dimensionful number, then you can no longer use dimensional analysis to say that h goes as t squared. For instance, you could have h goes as t, as shown here. And this corresponds to if you had a bubble that is of this size, the size of the initial dominant node, and it starts to rise. The height goes as t squared initially, but eventually it hits its terminal velocity. And then it would continue to rise much as shown here. Now in my simulations, I showed you this animation, and you saw that the size of the bubbles actually increases with time, and when the size of a bubble increases, its terminal velocity should also increase, and that's why people normally think that h should go as t squared. But despite this, in my simulation, it seems like h goes as t. And if you look at the simulation that Jim Stone did of the Rayleigh-Taylor Instability, you'll see that for their simulations too, also using Athena, the height is increasing as t, not as t squared.
Is the background fluid away from the interface stratified?
In their case, no. So in their case,
in your case, yes.
In my case, yes.
So the deformations are becoming comparable in size to the scale height of the background, yes.
So these two simulations, the solid line is without stratification, and the dashed line is with stratification. And this is because my h over L is very large, so things are rather Buoyancy. And that's also the limit that Jim Stone used when he did these simulations. So I got a linear increase of height with time. So did Jim, although he didn't in his paper he didn't plot it on a log scale. So he didn't identify this, but if you look at other codes, the height does increase quadratically with time. So for some reason, Athena gives a different result, and it's unclear to me why this is the case.
Are the other codes fully compressible?
So you can do this problem with Flash, which is a fully compressible code, and you get that h goes as t squared. I should say that Flash probably used a different initial perturbation than what I used. I have tried running this problem with the same initial perturbation with a code called Maestro, which is developed by LBL, Lawrence Berkeley Lab, and their code is kind of anelastic, so it kind of looks like it's incompressible. So in that case, I got with the same initial perturbation, I got that the height went as t squared. If the differences are due to slight changes in the initial perturbation, that's pretty troublesome in and of itself. But I really can't see any reason, I can't seem to
with the same,
solve this
same
discrepancy.
initial conditions.
Yes, same initial conditions. Yeah. So the simulations I ran, and the simulations that Jim ran, they use a different initial perturbation as Flash. Flash gets h goes as t squared. In Athena, you seem to get h goes as t. When I did the same initial perturbation for a different code that isn't fully compressible, I got h goes as t squared. And I assumed that if I tried to do it in Flash with the same initial perturbation, I would also get h goes as t squared. So to conclude, I hope I've convinced you that anisotropic conduction is important in several astrophysical contexts. Linearly, the growth rates don't change much unless you are compressible, and if you are compressible, it only changes if the density contrast is small. In the nonlinear regime, there's kind of these three effects: diffusion, Rayleigh-Taylor instability, and this heat-flux-driven buoyancy instability. And then the kind of disturbing thing is that the results depend on which code you use. So the real moral of the story is that the Rayleigh-Taylor instability is hard to do numerically because you have an unresolved discontinuity. And I think that that's the problem with that's causing this discrepancy. It's good theoretically because it's kind of a discontinuity is kind of the simplest sort of gradient that you can come up with. So you can do the linear theory very nicely, but the nonlinear dynamics, I'm not sure that I trust any of this. Thank you.
More questions? I have a question. So that plot, the log scale, it was quadratic for a bit.
Yeah.
So
I'm not sure if I
reckon
believe
that
this being quadratic. It could just be the initial exponential growth. But
yeah. So you could, and perhaps, if you wait long enough in another code, you'll see something that's linear, and if you fiddle with the knobs enough, you could see something, a quadratic case lasting longer.
Right. Yeah. So that's one thing. Another thing is that when you're plotting on a log plot, there's kind of you can get things that are a bit confusing looking depending on where kind of the origin of time is. So that can shift the slope. So in other codes, what you get is you get the codes that I think the height actually going as t squared when you plot on a log plot.
It's one of the time derivatives in though, you get rid of the word.
What you end up with, so this is log h versus log t. If this is t squared and this is t, you get something that looks kind of like this. Okay, so you approach t squared as you go to later times, and my guess is that if you went for a really long time, then you would actually get t squared. This is the opposite case. I mean, you actually go from t squared to t, so it's the opposite transition. This sort of transition is not what you would predict if you thought that you got the offset of t. If you did like t minus t naught.
So have you done a resolution test where you fix the initial conditions?
The same initial conditions for different resolutions. So I use for all the resolutions, I do the same zone-to-zone random number with a vertical smoothing. So in all the simulations, it's kind of the same thing. So that there is kind of power at higher.
As you scale up the number of cells, you are scaling down the
right. Yeah.
the noise you're adding in. So you could not do that.
Right. Yeah. So I have not done those simulations.
Similarly, you might want to put in physical viscosity.
Yes. Yeah.
Physical effect. And well resolved at your lowest resolution.
Yeah. So I played around a little bit with that, and it seems like the effect is basically that when you try to use a real explicit viscosity, then you end up with the same curve even when you increase resolution. So I think So I think you can explain this sort of behavior just from the fact that the viscosity is not explicit.
I have another question. So you talk about going to a Buoyancy limit for small K per or large K per times H. And of course that makes sense, you know, in that you can make things small enough so they become isothermal so that you can conduct quickly across there, and that's going to be very unstable. But what about, you have to check the KZ that you have the formula for, right, that comes from solving the problem outside. And if that thing is, if the vertical scale is scale height or so, then those will still be compressible.
So let's see if we can, so if KH is large, you can divide everything in these equations by K, and basically the important term will be this one.
Right, but it depends on R, I guess, as well, right? So,
Yeah, it's this term and yeah, so you end up with a balance between this term and this term. So yeah, so you can check carefully to see if these KZs are actually small, and I think when you do that, the answer is yes, they are small.
Anything else? Okay, well, then we will have cookies upstairs, and we will thank you again, I guess.